Hello everyone. Welcome back to another video in the neural network series. Today we'll be programming a backpropagation method for our neural network. Last time we made a forward propagation function, which is really the main way that a neural network processes information and returns the outputs that it does. However, if you remember from our video, the outputs that we got were pretty meaningless, and that was because the network hadn't been trained yet. And so backpropagation is really the key algorithm responsible for allowing the neural network to train itself. The basic idea behind the backpropagation algorithm is that we're going to take the output that we get from our network and compare it to the desired output and then calculate some sort of loss metric on it. And then this loss is then propagated backwards through the network, and we then calculate the amount by which we want to change each of our parameters, namely the weights and the biases, to most effectively decrease our loss. This is a very, very famous algorithm, and most of the math behind it is um, chain rule and just some basic matrix multiplication. So if you'd like a more detailed video on the math behind backpropagation, I've linked a video in the description that I think does a pretty good job. Okay, let's dive into the code now. I will begin by making a function that is basically the derivative of our ReLU activation function. We need this derivative as it ends up popping up when we do our chain rule in backpropagation. The method itself is pretty straightforward to code. If our input is positive, then our derivative is 1. Otherwise, the derivative is 0. And this is due to the fact that the ReLU function is a piecewise function. Cool. Um, we're going to use a sort of a neat trick uh, to implement the piecewise nature of this function. Instead of using an if-else statement, we're going to use the NumPy where functionality, which essentially is an if-else function, except it's vectorized, so it mitigates the use of a for loop. Cool. Now we can begin our backpropagation function in our network class. One quick change that I did make from the last video was that I made the activation class object f a class attribute. So now we can access it throughout the class without having to redefine it every single time. Note that, however, now you do have to call it with a self in front of it, so in self.f instead of just f. Okay, so let's start by filling in the arguments that this function will take in. We will need to pass in self, obviously, and also x, which is going to be the input, and y true, which is going to be the desired output. Cool. Now, the first thing we're going to need is the derivative with respect to the cost function. The cost function we're going to use in our case is the 2 norm, which is essentially the squared, the sum of the squared difference between the desired value and our predicted value. And the derivative of this function is pretty straightforward. It's simply going to be 2 times the predicted output minus the desired output. Next, we will go ahead and find out the error terms. You can do this iteratively using a for loop, or personally, since we just have 4 layers, I'm going to be hard coding them in. But as the number of layers in your neural network increases, it might be a good idea to switch to using a for loop. Okay, so we begin by finding the error term of our last layer, so del4. This happens to be the same as the derivative of our loss, so del4 is just going to be equal to dc. Next, we'll find the error term of the third layer. Here we'll need to take the derivative of our pre-activation values with respect to our activation function, and we're going to do this for the pre-activation values in the third layer. And so we call self.f.drelu on self.z3. Then this gets multiplied element-wise by the weights in the fourth layer, specifically the transpose of the weights. And so we will call self.l4 for layer 4, dot weights, and dot t for transpose. And we use the asterisk here for element-wise multiplication. Cool. Then this will get matrix multiplied by the last layer error term. So in this case, del4. And we will use the at symbol for matrix multiplication. Now we just repeat this process for the other two layers. So going to the del2 term, we will do the same thing. We will have the derivative of the pre-activation values in the second layer, self.f.d relu self.z2. And then this would be element-wise multiplied by the weights in our third layer. So self.l4.weights.t for transpose. And then lastly, that gets matrix multiplied by the error term of our last layer. So at del3. Cool. So now we have found all our error terms, and we need to now find the gradients of all our parameters. These gradients will essentially tell us how much each parameter needs to be perturbed to decrease the error in our outputs. For each of the weights, all we need to do is matrix multiply the error term with the transpose of the activation values of the previous layer. And that will be del4 at self.a3.transpose, or .t for transpose. We will do the same for the weights in the third layer. And so del3 at self.a2.t. And then same thing for the second layer, del2 at self.a1.t. Cool. For the first layer, we will not be multiplying by the activation values. Instead, we'll simply be matrix multiplying del1 with x, our input value, specifically the transpose of x. Lastly, for the biases, the gradients are pretty simple. These are just our error terms themselves. So self.db4 is del4, self.db3 is del3, and so on and so forth. Cool. And so with that, we have found all our gradients using back propagation. And in the next video, we'll be implementing the gradient descent function that uses these gradients to actually change the parameter values themselves and actually train the network. Cool. I hope you all enjoyed this video, and I'll see you in the next one.